All right, 7.3 product and quotient laws of logarithms. At the very top of page 8, you have space for some notes. The first note we're going to take is a review or recall, and it is on the power law of logarithms. Recall, power law of logarithms. The power law of logarithms states that any log with a base of b, log of x to the power of n, what can we do to the exponent?
N log bx.
You can bring it down in front of the log. We would say this is the log of x base b times n. And there's always some rules that have to be true. B must be greater than 0. And also b can't be 1. It's because we're essentially finding the exponent that takes b to the power of x. Sorry, that makes b equal x. So b to the power of something equals x. So b can't be 1 because 1 to the power of anything is just 1. And here x also must be greater than 0. So some of the numbers are restricted to positive, being positive numbers. Today, we're talking about the product law and the quotient law of logarithms. I'm just going to write down the law and then we'll discuss. Product law of logarithms. Product law of logarithms states that the log of any base b of any number that can be divided into its factors, m times n, I can rewrite this log as the log of m base b plus the log of n base b. And similar restrictions apply. This only is true for b greater than 0, b cannot equal 1, and m and n are both greater than 0. The other law that we are going to be using is the quotient law. Quotient law of logarithms. Which you can probably take a pretty good guess at what it is if you look at the product law of logarithms and you're familiar with the product and quotient laws of exponents. Basically, if you can express this number as m over n, then you can replace that with a simpler statement to understand. Or it works vice versa, of course. But this would then be the log of m base b minus the log of n base b. And of course, one of the keys is that you're working with the same base each time. Good. Again, you could develop these ideas using the laws of exponent and applying them to the logarithms, and they'll come out. So you could define these algebraically or determine these algebraically. We're not going to bother with that. We're just going to use them. Okay, in example 1, we're asked to write these as single logarithms. So in A, I'll just copy it down while you think about it. Which laws are you going to apply, or what law can apply to example 1A? So we could go through the work of calculating the log of 6 base 5 and the log of 8 base 5 and the log of 16 base 5. but much easier. We can just apply the product and quotient law of logarithms. Apply product and quotient laws of logarithms. And they're both in here. So all we really need to remember is that we're writing the word log with the same base. And then I can combine the 6, the 8, and the 16 according to the operator that they have. So I combine the 6 and the 8 using the product law, and then I consider 16 using the quotient law. What I end up with is a log that has 6 times 8 in the numerator, 16 in the denominator. Which I can reduce to the log of, with a base 5. 6 times 8 is 48, divided by 16 is 3. So there I have simplified it into a single log. The second one says log of x plus the log of y plus the log of 3x minus the log of y. There are two methods that you could use. The first one would be, one of them is collecting like terms. So if you have logs of x or logs of y, you can clearly see plus 1 log y minus 1 log y. Those guys are going to cancel out. But what we could do is we could apply the product and quotient laws directly. So that's what we're going to do the first time. I'm going to apply product and quotient laws directly. In which case I notice they all have the same base. They're all common logs. So now I just need to be careful about how I write them inside my brackets. I've got x times y times 3x all in the numerator. So I've got x, y, and then in my bracket 3x. And because it's minus y, that makes its way into the denominator according to the quotient law. And then I can simplify this by canceling out my factors of y in the numerator and denominator. I have a factor of 3, and I have 2 factors of x. So I end up with the log of 3x squared. But because of what we know about relations, we need to have some restrictions on this. So this is only true where x is greater than 0 and where y is greater than 0. So just like when we worked with rational functions, if we end up with a restriction, we need to carry that through into our final answer. Okay. All right, the other way to do that would be to first simplify, comma, then apply laws. And basically all that means is that we're going to simplify first. So we're going to let log y, positive log y, eliminate negative log y, rewrite what we have, which would then be the log of x plus the log of 3x. And from there, we just have product law now. We don't even have quotient law. So I can rewrite that as a product, which should be x times 3x, which is 3x squared. And then, of course, remembering our restrictions. X must be greater than 0, y must be greater than 0. Yes. Again, once you're good at it, you can probably just skip straight down from here to here. You could probably even just in your head skip from what we have down to the very end. If you understand how these product law and quotient law work. It's example 1. Just a quick note on our restrictions. So restrictions come from the original expression. Restrictions, how do I want to say that? Restrictions are placed on the variable. Restrictions are placed on the variable according to restrictions on the original expression. Restrictions are placed on the variable according to restrictions on the original expression. So when you're writing down those restrictions, you need to look back at the original, which was log x plus log y plus log of 3x minus log of y, where you cannot take the log of a negative number or the log of 0. So that's where we find out that x must be positive and y must be positive. Example 2, we are asked to evaluate using the laws of logarithms. There are 3, A, B, and C, so that you can space yourself out. Here it is, log of 4 base 8 plus log of 16 base 8. So again, right away we notice that we have 2 logs with the same base. So which law are we going to apply if we have addition in between them? Product law of logarithms, because there's addition in between them. So we're going to multiply, I'm going to skip the middle step here, we're going to multiply 4 and 16, which gets us 64. So now we're looking at the log of 64 base 8. So what exponent of 8 will get us 8 to 64? 8 to the power of what is 64? 2. Okay, I'm going to stop showing work on things like that. But of course, what you could do if you weren't sure, you would express 64 as 8 to the power of 2. Then your question is, what exponent do I raise 8 to get 8 to the power of 2? Well, it's 2. B, the log of 405 base 3 minus the log of 5 base 3. Which law are we applying?
Quotient.
Quotient law. So copy down my log base 3. 405 divided by 5. Well, 400 divided by 5 is 80, and 1 more, so 81. That's helpful because 81 is a power of 3.
Yeah, so it's 3 to the power of 4.
3 to the power of 4. Okay, you can get 3 times 3 is 9, times 3 is 27. That's pretty straightforward. And then you can almost assume that it's going to be 4, but you should check it mentally. 27 times 3 is 81. So log of 81 base 3 is 4. 3 to the power of 4 is 81. Okay, there's a power law, product law example, and a quotient law example. And C is slightly trickier. It has one new step for us. We've got 2 times the log of 5 plus 1/2 the log of 16. In this case, if we're evaluating this, we don't see, I mean, we have logs that we can combine these guys, but we can't do that right off the hop because these logs, we can't combine them using our product law because they each have a multiplier stuck in front of them. Okay, so it's like we can't combine them because they're not by themselves. It's not just log 5, it's 2 times the log of 5. It's not just the log of 16, it's 1/2 the log of 16. So what is a strategy, or what can you think of in order to get rid of these multipliers in front of each log?
Well, you can move the multiplier to the n position.
Yeah, to the exponent.
Yeah.
You can make them an exponent. So it's still an application of the power law, but it's kind of used in reverse as to how we've been using it. So apply.
And for the 2 log 5, you can just put 25 there to make it easier.
Yep, we'll do all the steps for the example, but you're right, you would probably skip that in your practice problems. Apply power law. If you need help, you can, if you're not sure, you can kind of call it in reverse if you want to. It's not really reverse because it works equally well both ways. But if that's helpful, you can call it that. I'm okay with that. So what we're going to do here is we're going to make this the log of 5 to the power of 2. And we're going to add the log of 16 to the power of 1/2. Log of 5 to the power of 2, I can simplify that right away to the log of 25. What is the log? How could I simplify this one? 16 to the power of 1/2? What is 16 to the power of 1/2? What does that mean?
16 to the power of -2.
Different. It's the square root of 16.
Oh, yeah.
Okay, I'll write that step. I was gonna skip it, but we'll write it to remind us. Okay, so that right there tells you 16 to the power of 1/2 is the exact same as the square root of 16, which then the next step is fairly straightforward. Leave log of 25 plus the log of 4. Hopefully you can see that now. And now we can apply our product law. Apply the product law. We get the log of, I'll write every step, 25 times 4, which is the common log of 100. Common log always has a base of 10. So what do we raise 10 to get 100? Final answer is 2. Okay, the only real added tricky thing in this one was applying the power law in reverse, which brought our multiplier to be the exponent of the log. Example 3 says, write the logarithm of a product or quotient as a sum or difference of logarithms. So essentially what we're doing is we're taking now an ugly looking log and expanding it. There are 4 of them, A, B, C, D. And A looks like this. The log with a base of 3, the log xy with a base of 3. How would we expand this?
Log of x base 3 plus log of y base 2.
Nice. What law did you use?
Product.
All right, it's product law. And when we do this, we need to also remember our restrictions. So we look back at our restrictions, and I guess they could come from any step, really, anywhere along the way where we come up with restrictions. In order for this statement to be true, xy has to be greater than 0, which really means that if x and y were both less than 0, that would work just fine. But now that we've split it out this way, that doesn't work at all because x can't be negative and y can't be negative. So that becomes our restrictions. X is greater than 0 and y is greater than 0. B is the log of 20. And so we're going to split this thing up. Now, there are 2 ways to do this one. Why? Well, because 20 has more than one way to split it into its factors. Okay? So one answer could be, you could express, I'll split it up. You could express it as 4 times 5. in which case you would get the log of 4 plus the log of 5. But there is a way that might be more helpful, and what would that be?
We can do the square root of 20 if you're really brave. Or what, 2 times 10?
We can do 2 times 10. Why might that be more helpful? I'm going to write it as 10 times 2, which translates into the log of 10 plus the log of 2. What do you know about the log of 10?
It's 1.
It's just 1. So in some ways, this is more simplified, I suppose. If you can get all the way down to 1, that's helpful. But they have the exact same value, these statements. Okay? C is, essentially this is just practice in using the laws that you've just learned. So we've got the log of a b squared c. Go ahead and split that one using the product law and simplify it. In the first step, you should end up with the log of a plus the log of b squared plus the log of c. What else could we still do?
We can do log a plus 2 log b.
Yeah, we can take this exponent using the power law of logarithms and bring it down in front. So now you've got the log of a plus 2 times the log of b plus the log of c. D is going to introduce a bit of quotient law work. It is the log of u v over the square root of w. Give that one a shot. You can do it step by step.
The hardest part here is that my u's and b's look exactly the same.
Okay. This should end up with log of u plus the log of v minus the log of radical w.
Or you can do w to the 1/2.
Good. So you,
Log w.
yep. So it's a 3-step process that you could probably do in 2 steps or even in 1 step. I'm going to rewrite my square root of w as w to the power of 1/2 because now I can see that I can apply my power law of logarithms to get the log of u plus the log of v minus 1/2 the log of w. So you can, oh, in restrictions, we didn't do our restrictions on our last one, but u must be greater than 0, v greater than 0, w greater than 0. In the one above that, a, b, and c all have to be greater than 0. All right, and you can kind of get a feel for what is considered to be the most simplified form of a log. We don't like radicals. We don't like exponents. We want it just one clean line with multipliers in front is the easiest way. But if you had to take this now and express it as a single log, you'd be working backwards to get that. Okay? All right, in example 4, just more simplifying. So we've got a, which is the log of, and then a big bracket with a numerator of radical x and a denominator of x squared. Now there are 2 strategies that could be used to simplify this. Can you identify the 2 strategies? I'll give you a hint. They both start with quotient law. One is the quotient law of logs. The other one, I could simplify this bracket using the quotient law of exponents first. Again, we'll do it both ways, and then you can see which one is easier. In my opinion, the quotient law of exponents is quite a bit easier, but we're going to use the quotient law of logs. Quotient law of logs, and then over here we'll use quotient law of exponents. So first, quotient law of logs. Basically what it says is that we can now take the log of radical x minus the log of x squared. And then we can simplify. We can change this radical into x to the power of 1/2. Again, I'm writing every step. There probably are some steps here that you'd be able to skip in your work. And now I'm going to use the power law of logarithms, which allows me to bring 1/2 times the log of x minus 2 times the log of x. And now I'm working with, I have the same variable part on both, and I'm adding, subtracting fractions. So I need a common denominator. So I'm going to express 2 as a fraction over 2, which would be 4/2. Now I have 1/2 minus 4/2. That's negative 3/2 times the log of x. My restriction, x must be greater than 0. All right, that was 1, 2, 3, 4, 5 steps. Let's see if we can do it with the quotient law of exponents first. So basically what that means is you're going to simplify inside the log bracket here and then go from there. So what does that look like? That means we get this equals the log of, I'm going to rewrite my bracket as x to the power of 1/2 over x squared. Then I'm going to express this as using the quotient law of exponents, which means that if I have two powers with the same base, one over the other, divided by the other, I can subtract the exponents. So what I actually have here is x to the power of 1/2 minus 2. Again, showing every step possible. I'm adding and subtracting fractions, so I need to express 2 as a fraction over 2. So I've got 1/2 minus 4/2. That gives us the log of x to the power of negative 3/2. And then I can apply my power law of logarithms, which gives us negative 3/2 times the log of x, where x must be greater than 0. So you can decide what you like more. They're the exact same calculation is needed because we had 1/2 minus 2, which is exactly what we have here. So you have to still add and subtract fractions, which is what we did, and then you still have to apply the product law. Here we did it later, and here we did it earlier. B. There are 3 of them, by the way. B is the log of, in brackets, radical x, square root of x, and then we're going to raise that square root to the power of 3. We're going to add the log of x squared, and we're going to subtract the log of radical x. Now again, there's more than one way to do this. What we're going to do is express all of these. This is x to the power of something, x to the power of something, x to the power of something. Okay, and then we'll use the product and quotient law of logarithms. So first step is to rewrite this using exponents. So we are going to end up with the log of, do you know how to express this thing if you have the square root of something to the power of 3? Well, the square root of x is really x to the power of 1/2. So the the power of powers law tells you that if you have x to the power of 1/2 to the power of 3, you can multiply your exponents, which will give you 3/2. So this is x to the power of 3 over 2. This is the log of x squared. This is the log of x to the power of 1/2. And from there, we can apply the product and quotient laws of logarithms. So we're going to combine this into one log. It's kind of a bigger log with a big bracket there. In the numerator, we're going to have x to the power of 3/2 times x squared. In the denominator, we're going to have x to the power of 1/2, right? Now that we've got it set up in here using the laws of logarithms, now we have a bunch of exponents together within that log. So now we're going to apply the law of exponents. So I'm just going to put from here to here, we applied laws of logs. But now from here to, it's going to be about the same size. We're going to apply the laws of exponents. So what's that going to look like? Well, wherever we are multiplying powers with the same base, we can simply add the exponents. And when we're dividing a power with the same base, we can subtract the exponents. And at the same time, I know I'm going to be working with halves, so I'm going to express this 2 as 4 over 2. Okay? So here we go. We've got the log of x to the power of 3 over 2 plus 4 over 2 minus 1 over 2. That is 3/2 plus 4/2, that's 7/2, minus 1/2 gives us 6/2, which gives us 3. So we're looking at the log of x cubed. Is that as fully simplified as we can do? We got one more step, right? Product law. Power law of logarithms says we can rewrite this as 3 times the log of x. The only variable here is x, so x must be greater than 0. Done. Good, good. C is the log of 2x minus 2 minus the log of x squared minus 1. All right, this one is a bit uglier, a bit trickier. It brings in new considerations for restrictions on the variable. But again, you can see we've got a subtraction between two logs with the same base, so we're going to be using the quotient law. And then you can even see a product law within each of these. Both of these logs can be factored. Okay, so let's go step by step. First thing we're going to do is apply the quotient law.
Sorry, can I talk to Mr. F quickly?
So we can rewrite this as a single log with 2x minus 2 in the numerator and x squared minus 1 in the denominator. And then again, you're kind of looking at this and saying, okay, what can I actually do? And from here to the next step, we're actually going to factor numerator and denominator. So when we factor the numerator, we end up with 2 times x minus 1. And that's convenient because when we factor the denominator, which is a difference of squares, we end up with x plus 1 x minus 1. And then you can see that within that log, one of the factors in the numerator and denominator cancel out, but we're going to need to remember it for our restrictions, which we'll talk about in a sec. So here we go. We've got now the log of 2 over x plus 1. And that is as simplified as we're going to get. Now, to determine the restrictions, we need to consider the original equation. To determine restrictions, comma, consider the original expression. So if we look at that expression, in order for this whole expression to be defined, two things have to be true. 2x minus 2 has to be greater than 0, and x squared minus 1 has to be greater than 0. So all we're doing is determining our restrictions on x, but x is involved in both of these logs, and x can only be one thing at a time, so both of them need to be defined. Both of them need to hold true. So if we work this through, we're going to add 2 to both sides and divide by 2. So we get 2x is greater than 2, x is greater than 1. Okay, that will satisfy our first log. In our next log, we're going to add 1 to both sides. So we get x squared is greater than 1. But there are two possibilities for this. In order for x squared to be greater than 1, either x has to be greater than 1. 1 times 1 is 1, so anything bigger than 1 will, multiplied by itself, will be bigger than 1. But also, x could be less than negative 1. Any number with an absolute value greater than 1, but if you multiply it by itself, it's a negative times a negative, which is a positive. Okay? So all of these are possible as well. Now, which restriction makes both of these pieces true? Well, they're both true for x greater than 1. If x is less than negative 1, it works for this log, but not for this log. Okay, so we have to impose x greater than 1 on the whole expression. Since both logs are defined for x greater than 1, this is the restriction on the expression. Therefore, I'm just going to rewrite the question that we started with and our final solution. The log of 2x minus 2 minus the log of x squared minus 1 is equal to the log of, in brackets, 2 over x plus 1, where x must be greater than 1. Okay, this restriction ensures that all logarithmic expressions in the equation are defined. That's that. You can find your practice problems at the bottom of the page there in your notebook.